Space looks silent, empty, and endless, but the deeper mathematics tells a stranger story. A beam of the light can bend without touching anything. Two paths that seem parallel may one day meet, and a universe that appears flat could still loop back on itself, hiding its true shape beyond every telescope we can build. Is space infinite, gently curved, or finite with no edge at all? This journey follows ancient light from the cosmic microwave background, the delicate balance of matter and energy, and the possibility that inflation stretched the universe until its curvature nearly disappeared. If this kind of calm scientific mystery brings value to your evenings, please like the video, subscribe, and share it with someone who enjoys quiet questions about the cosmos. Thank you for spending part of your time here. What time is it where you are, and where are you watching from? Leave a comment below. Now, let the visible universe become our measuring instrument, and step into the hidden geometry of space. Space often appears to be the simplest part of the universe. It seems like the absence between things, a silent interval separating stars, planets, galaxies, and every smaller object held within them. In ordinary life, empty space feels passive. A room can be cleared, a field can be left open, and a container can wait to be filled. From that familiar experience comes an ancient and powerful picture of the cosmos. Matter performs its movements. Light crosses the darkness, and space merely provides the stage. Yet modern physics replaces that picture with something far stranger. Space is not only where events happen. Together with time, it forms a physical structure that can change, respond, ripple, stretch, and guide motion. The universe does not unfold inside a rigid emptiness. Its emptiness participates. This shift begins with relativity, which treats space and time as parts of a single geometry called space-time. Geometry usually describes shapes and distances, but in relativity it also describes gravity. A planet does not pull a nearby moon through an invisible force acting across a passive void in quite the old Newtonian sense. Instead, the planet changes the geometry around it, and the moon follows the straightest path available through that curved region. The path looks bent when viewed from outside, but within space-time it is a natural route, much as a ship can follow what seems like a straight course across the curved surface of Earth and still trace an arc on a flat map. The comparison is limited because space-time has more dimensions and a more complex structure than a planetary surface. Yet it captures the essential reversal. Gravity is no longer placed on top of space. Gravity becomes a feature of space and time themselves. This geometry is not fixed. Matter and energy shape it, while the shape of space-time influences how matter and energy move. The relation is mutual and continuous. A star alters the paths of nearby planets. A black hole produces far more extreme curvature, forcing even light to follow paths that can no longer escape once they cross a certain boundary. A galaxy bends the light of objects behind it, sometimes producing stretched arcs, multiple images, or luminous rings. These effects are not tricks of perspective. They are direct evidence that the route through space depends on the geometry of the region being crossed. Light, which has no rest mass, still responds because it follows space-time rather than obeying a simple pull on matter alone. The emptiness between source and observer therefore has measurable structure. Relativity also predicts that space-time can carry disturbances. When massive bodies accelerate in changing arrangements, they can send ripples outward. These ripples are gravitational waves, moving deformations in space-time itself. They are not waves travelling through space in the same way that sound moves through air. They are changes in the pattern of distance and time, passing through regions that may contain almost no matter. When such a wave crosses a detector, the lengths of perpendicular paths change by an almost unimaginably small amount. The effect is subtle, but its meaning is profound. Space is not an unmoving background. It can oscillate. It can transmit information about collisions between black holes or the final motions of dense stars. The stage does not merely support the drama. The stage can tremble. Space-time can also expand. On the larger scales, distant galaxies are not simply flying through a pre-existing emptiness as fragments from an explosion. The distances between widely separated regions increase because the geometry itself changes with cosmic time. This does not require every local system to stretch. Galaxies remain bound by gravity, stars remain intact, and atoms do not swell with the universe. Expansion becomes important across vast intergalactic distances, where the overall fabric of cosmic geometry evolves. As the expansion continues, light travelling through space is stretched to longer wavelengths, carrying a record of the changing scale of the universe. Once again, what appears to be nothing behaves like something. It defines distance, and distance can grow. Curvature, waves, and expansion sound like separate phenomena, but they belong to one deeper idea. Space-time possesses geometry, and that geometry is dynamic. In a sufficiently small region, far from strong concentrations of matter and energy, space-time can look almost flat. In flat geometry, freely moving objects that begin along parallel paths remain parallel, provided no other influence intervenes. The rules resemble the geometry learned from ordinary drawings, where straight lines continue without meeting, and the angles inside a triangle add to a familiar total. But this local simplicity does not guarantee that the universe as a whole is flat. A small patch on the surface of Earth also looks flat. Roads can be built. Squares can be drawn, and short distances can be measured without noticing the planet's curvature. Only when the scale becomes large enough does the wider shape reveal itself. The same caution applies to the cosmos. Local measurements can show nearly flat space-time, even if the total universe follows a different geometry on scales beyond immediate reach. Near massive objects, positive forms of curvature cause paths that begin parallel to move toward one another. Around a star, the effect is gentle. Near a black hole, it becomes dominant. Another mathematical possibility is negative curvature, in which paths tend to spread apart more quickly than they would in flat space. These descriptions are easiest to picture using surfaces, though the actual universe is not a thin sheet embedded in a higher room. A sphere offers a model of positive curvature. Lines that begin parallel near the equator can meet at a pole, and large triangles contain more angular width than flat triangles. A saddle offers a model of negative curvature. Paths diverge, and triangles contain less angular width. Flat geometry lies between them. These models are not literal portraits of the universe, but they reveal that geometry can be tested from within. No outside vantage point is required. Observers need only examine how distances, angles, and light paths behave across large regions. The distinction between local and global shape is crucial. Space-time near Earth is curved by Earth, the Sun, the galaxy, and larger structures. Yet these local distortions do not by themselves answer the question of the universe's overall curvature. A landscape can contain hills and valleys, while belonging to a planet whose broad surface has a simple global form. In a similar way, the cosmos contains intense pockets of curvature, while still possessing an average geometry that may be flat, positively curved, or negatively curved across the greatest scales. To discover that average, cosmology smooths over individual stars and galaxies and asks how the universe behaves when matter is viewed as a vast distribution rather than as isolated objects. At that scale, the question becomes one of balance. The contents of the universe determine the evolution of its geometry, while the measured geometry helps reveal the total contents. This is where the familiar image of empty space finally breaks apart. Space is not a warehouse waiting for objects. It is not a theatre floor that remains unchanged while the performance continues above it. It is woven into every measurement of motion, distance, duration, and gravity. It can bend around matter, carry waves from ancient collisions, and expand between remote galaxies. Even a region with almost no particles still belongs to this structure and can possess curvature, energy, and a changing scale. The apparent emptiness has rules, memory, and motion. This physical structure is not material in the ordinary sense. It is not made of atoms, dust, or a hidden fluid flowing between galaxies. Its reality appears through relationships which events can influence one another, how clocks compare, how light travels, and how freely falling bodies trace their paths. Space-time is therefore less like a substance placed among objects and more like the changing framework that gives location, separation, and sequence their meaning. Yet this richer picture immediately opens a larger mystery. If space-time can curve in local regions, then the entire universe may also have a broad geometric form. It may close upon itself, extend without limit, or repeat through a topology that hides its boundaries. The answer cannot be obtained by looking at space from outside, because no confirmed outside position exists. It must be inferred from within, using light that has crossed enormous distances and patterns left from the earliest observable eras. Before those measurements can be understood, the old idea of empty space must be surrendered. The cosmos does not contain a silent stage beneath its events. The geometry is one of the events. Matter does not bend space-time in the way a heavy object dents a rubber sheet resting in a room. That familiar image can suggest the right direction, but it hides as much as it reveals. A sheet bends downward because gravity already exists outside the sheet, while space-time does not require a second gravity pulling it into some surrounding dimension. Its curvature is intrinsic. Distances, durations, and possible paths change from within the geometry itself. A massive body alters the way nearby events are connected, and every freely moving object responds by following the most direct route that geometry allows. The result appears as attraction, orbit, falling, or deflection. But beneath those motions lies a quieter rule. Matter and energy shape space-time, and shaped space-time guides matter and energy. Around Earth, this effect is weak enough to feel ordinary. A released stone accelerates toward the ground. A satellite remains in orbit because it falls continuously while moving sideways fast enough to keep missing the surface. In the older description, Earth exerts a force across space. In relativity, Earth changes the local geometry, and both stone and satellite follow natural paths through that curved region. These paths are called geodesics, meaning the straightest possible route through a given geometry. On a flat plane, a geodesic is an ordinary straight line. On a sphere, it becomes part of a great circle, such as the route traced by the equator. In space-time, the geodesic includes motion through time as well as motion through space. A planet orbiting a star is therefore not being forced away from a straight path in the deepest sense. It is following the straightest path available through curved space-time. This idea becomes easier to recognize when several nearby objects fall together in a sufficiently small region. All of them appear weightless because each follows its own geodesic. Astronauts in orbit float not because gravity has vanished, but because the spacecraft and everything inside it fall along nearly the same curved path. The feeling of weightlessness arises from shared free fall. Weight appears when a surface prevents that natural motion. The ground pushes upward against a standing body, stopping it from following the geodesic that would continue toward Earth's center. What feels like the force of gravity at the surface is therefore partly the resistance to free fall. Relativity overturns the ordinary intuition so completely that falling becomes the unforced state, while standing still requires continuous support. The curvature created by matter is not determined by mass alone. Energy, pressure, and momentum also contribute. A beam of light carries energy and therefore participates in gravity, even though light has no rest mass. Dense radiation can affect the expansion and curvature of the universe. Pressure inside an extreme object can help shape the surrounding space-time. Motion itself matters because the distribution and flow of energy enter the equations. The source of curvature is therefore broader than visible substance. Stars, gas, dark matter, radiation, and the energy associated with empty space all influence cosmic geometry in different ways. This wider meaning becomes essential when the question shifts from a single planet to the universe as a whole. Curved space-time also changes the behavior of clocks. Near a massive object, time passes more slowly relative to time farther away. This is gravitational time dilation. The effect is tiny across ordinary human distances, yet it is measurable and practical. Clocks at different altitudes do not remain perfectly synchronized because Earth's gravitational field affects them differently. Satellites used for navigation experience both gravitational and motion-related shifts in time, and their systems must account for those differences. The geometry of space-time is therefore not an abstract correction applied only near black holes. It influences technologies operating around Earth. Gravity changes not only where objects move, but how much time separates one event from another. Light also reveals curvature with unusual clarity. As a ray passes near a massive body, its path bends. The ray is not slowed and pulled sideways in the manner of a thrown object moving through air. It follows a null geodesic, the natural route available to light in curved space-time. During a solar eclipse in the early 20th century, measurements of starlight passing close to the Sun offered an early test of this prediction. Later observations transformed the effect into a major astronomical tool. A galaxy or galaxy cluster can act as a gravitational lens, bending and magnifying light from objects far behind it. When the alignment is close, the distant source may appear as arcs, rings, or several images arranged around the foreground mass. These patterns allow astronomers to estimate how matter is distributed, including matter that emits no light. Curvature becomes a map of the invisible. Dark matter reveals itself not by glowing, but by shaping the routes along which light travels. In especially massive galaxy clusters, lensing can expose concentrations of mass that do not match the locations of hot gas or luminous stars. The geometry records the total gravitational influence, whether or not the source is directly seen. Near a black hole, the same principles become extreme. Matter compressed into a sufficiently small region produces a boundary called an event horizon. Beyond that boundary, every future directed path leads farther inward. Escape becomes impossible not because an outward moving object lacks enough engine power in the ordinary sense, but because the geometry no longer contains an outward route that reaches the distant universe. Light cones, which represent the possible directions that signals can travel, tilt inward. The black hole is therefore not simply a dense object exerting a very strong pull. It is a region where space-time is arranged so severely that the future itself points toward the interior, outside the horizon. Light can orbit temporarily along unstable paths, and background images can be twisted into bright rings around a dark central region. These effects again show that geometry directs motion without requiring a material medium. Yet curvature does not always announce itself through dramatic environments. It is present wherever energy exists, though often at levels too small to notice. A human body contributes an immeasurably tiny amount, A mountain contributes more. Earth dominates nearby. The sun shapes the paths of planets across the solar system. The galaxy governs the long movement of stars, while vast structures influence one another over millions of light years. Geometry has no single scale. It is layered, with local distortions set inside broader ones. A spacecraft leaving Earth does not pass from curved space into perfectly empty flatness. It moves from one pattern of curvature into another, gradually leaving Earth's influence while remaining within the suns, the galaxies, and the wider cosmos. Relativity also predicts that changes in curvature do not spread instantaneously. When massive bodies move in an uneven and accelerating arrangement, the changing geometry travels outward at the speed of light as gravitational waves. A pair of black holes spiraling together loses orbital energy through these waves, approaches more rapidly, and finally merges, far away. The passing disturbance alternately stretches and compresses distance along different directions. The change is extraordinarily small by the time it reaches Earth, but sensitive instruments can detect the pattern. Such detections confirm that space-time is not only curved, but capable of carrying motion in its curvature. The geometry remembers distant collisions as faint travelling ripples. The source and the path cannot be separated cleanly. Matter shapes the geometry that carries the signal, and the signal itself is a change in geometry produced by moving matter. This circular relationship is one of the deepest features of relativity. It removes the old division between objects and the stage around them. The stage responds to the objects respond to the stage, and together they form a single evolving system. Even so, local curvature does not settle the shape of the entire universe. Earth, the sun, black holes, and galaxy clusters create hills and wells in space-time. But cosmology asks what remains after these irregularities are averaged over immense distances. A landscape may contain countless slopes while still belonging to a broadly flat plane, a closed surface, or an open one. The universe may be locally distorted everywhere and still possess a simple large-scale geometry. The first task is therefore to understand how individual concentrations of matter bend nearby space-time. Only then can the larger question emerge whether all those local distortions rest within a cosmos that is globally flat, curved inward, or curved in a way that spreads without closure. The universe may be locally uneven and still possess a simple geometry when viewed across the greatest scales. Stars, galaxies, and black holes produce their own regions of curvature. But cosmology asks what remains after those smaller structures are averaged into a broad cosmic pattern. That question leads to three basic possibilities. Space may have positive curvature, zero curvature, or negative curvature. These terms do not describe emotional qualities, nor do they mean that the universe must be shaped like an ordinary object floating inside a larger room. They describe how distances and directions behave within space itself. Positive curvature is often introduced through the surface of a sphere. A sphere is only a two-dimensional analogy, but it reveals the essential idea. On a flat sheet, parallel lines remain the same distance apart. On a sphere, lines that begin parallel can eventually meet. The meridians on Earth provide a familiar example. They are separated at the equator, yet they converge at the poles. Triangles also behave differently. A triangle drawn across a large enough part of a sphere can contain angles whose sum is greater than the flat geometric total. None of this requires the surface to be viewed from outside. The curvature can be discovered by measurements made entirely within the surface. A traveller can compare paths, angles, and distances and conclude that the world is curved even without seeing the planet as a globe. A positively curved universe would follow a related principle in 3 dimensions. Its geometry would cause initially parallel paths to tend toward one another across sufficient distance. If the curvature were uniform and the topology simple, space could be finite without possessing an edge. Movement in one direction might eventually return to the starting region, not because a wall had been reached and crossed, but because the geometry closed upon itself. The surface of Earth again offers an analogy. It has a limited area, yet there is no boundary where the surface suddenly ends. A ship can continue along a great circle and return to its point of departure. A closed universe could behave in a higher dimensional way, although its true structure would not resemble a ball with an interior and exterior in ordinary space. Positive curvature therefore allows a cosmos that is finite yet unbounded. This combination feels strange because everyday objects usually become finite by having edges. Curved space can avoid that logic. It can contain only a limited volume while offering no terminal boundary. A path continues, but the continuation eventually folds back through the global geometry. Such a universe might be compared loosely to a cosmic loop, though the actual possibilities are richer than a simple circle. The shape could be smooth and symmetric, or it could possess a more complex topology, the mathematical pattern describing how regions connect. Curvature gives one part of the answer, while topology gives another. A positively curved universe does not have to be a perfect higher dimensional sphere, but positive curvature narrows the family of structures it might possess. Zero curvature describes flat space. In flat geometry, the familiar rules of ordinary Euclidean mathematics apply across the region being considered. Parallel lines remain parallel. Large triangles have the expected angular sum. The circumference of a circle has the familiar relation to its radius. Distances grow in a straightforward way without the focusing of positive curvature or the spreading associated with negative curvature. On sufficiently small scales, almost any smooth geometry appears flat, just as a tiny patch of Earth can resemble a level plane. The cosmological question is whether this flat behavior continues across the observable universe and perhaps beyond it. A flat universe is often assumed to be infinite, but flatness alone does not establish infinity. The simplest flat space extends forever in every direction, with no edge and no return. Yet flat space can also be finite if its topology connects distant boundaries. A flat map can be imagined with opposite edges connected, so crossing one side leads back through the other. Such a map is often represented as the surface of a torus, but the flat space itself does not need to bend through a surrounding dimension in order for the connections to exist. In 3 dimensions, a finite flat universe could repeat in several directions. Light might travel around the cosmos and return from another side, producing repeated images of the same distant structures. The universe could then be flat in geometry while finite in volume. This distinction between curvature and total size is one of the most important in the entire problem. Geometry determines local and large-scale rules of measurement. Topology determines how the whole space is connected. One does not automatically reveal the other. Negative curvature forms the third possibility. Its common analogy is a saddle-shaped surface, bending upward in one direction and downward in another. On such a surface, paths that begin parallel tend to separate. Triangles contain a smaller angular sum than they would in flat space. Circles expand more rapidly with radius, enclosing more area than a flat circle of the same radius. In a negatively curved 3-dimensional universe, volume would grow faster with distance than it does in flat geometry. Space would seem to open outward, providing increasingly more room as larger regions were considered. This is sometimes called an open geometry, though the word open can become misleading because it does not necessarily settle every question about topology or cosmic fate. A negatively curved universe is often infinite in simple models, but more complicated finite topologies are mathematically possible. Again, curvature and extent refuse to become identical. These three cases can be described through the behavior of initially parallel trajectories. Positive curvature brings them together. Flat geometry keeps them at constant separation. Negative curvature drives them apart. The same distinction appears in triangles, circles, and volumes. Each test is a different expression of the same underlying structure. Yet the actual universe complicates these clean categories because it is filled with matter arranged in clumps. A triangle passing near a galaxy cluster may be distorted by local gravity, even if the average universe is flat. A light ray can be focused by a foreground mass while still travelling through a cosmos whose global curvature is negative or zero. Cosmologists therefore search for patterns across enormous scales, where individual irregularities can be modelled or averaged. The goal is not to declare that every location shares identical curvature in every detail. It is to identify the broad geometry underlying the cosmic landscape. The distinction between space and spacetime also matters. Cosmic curvature is often discussed as though only space were involved, but relativity joins space with time. The universe evolves, so its geometry changes as it expands. A spatial slice taken at one cosmic moment may be described as positively curved, flat, or negatively curved, while the full spacetime includes the history of expansion as well. The classification isolates one important property, the large-scale curvature of space at a given stage of cosmic evolution. That property is connected to the total density of matter and energy, but it is not simply a visual shape that could be photographed from outside. No external camera is required, and no surrounding emptiness is assumed. The answer is written into internal measurements. If space has positive curvature, enormous triangles should carry extra angular width. If space is flat, their geometry should match the Euclidean rule. If space has negative curvature, their angles should fall short. Similar evidence can appear in the apparent sizes of known patterns, the spacing of distant structures, and the way light crosses the expanding cosmos. The universe reveals its shape through behavior rather than silhouette. The three possibilities therefore stand as more than abstract mathematical choices. A closed positive geometry suggests a cosmos that may return upon itself. A flat geometry suggests exact balance in spatial curvature, but leaves infinity unresolved. A negative geometry suggests a space that opens more rapidly with distance, yet still does not guarantee a simple, endless expanse. Each possibility changes the meaning of separation, direction, and scale. None can be judged by intuition formed inside rooms, landscapes, or planetary surfaces. The cosmic shape hides not because it lacks consequences, but because observers are embedded within it. Every ruler, clock, telescope, and beam of light belongs to the geometry being measured. The next step is therefore not to search for an outer view, but to build the largest possible triangles from ancient light, and allow the universe to disclose its curvature from within. The universe carries an ancient picture of itself, not as a photograph in the ordinary sense, but as a faint field of microwave light arriving from every direction. This light is the cosmic microwave background, the cooled afterglow of a time when the young universe first becomes transparent. Before that transition, matter and radiation remain locked together in a hot, dense plasma. Light cannot travel freely because charged particles scatter it again and again. As the universe expands and cools, electrons join with atomic nuclei, most commonly hydrogen nuclei, and the scattering becomes far less frequent. Photons begin to cross space almost undisturbed. They continue travelling while the universe expands around them, their wavelengths stretching from visible and infrared scales into the microwave range. Billions of years later, that radiation forms the oldest electromagnetic signal that can be observed directly. It comes from a spherical boundary around every observer, a last scattering surface marking the regions from which those ancient photons begin their long journey. The cosmic microwave background appears nearly uniform, yet it contains tiny variations in temperature. These variations are not random imperfections. They record differences in density, motion, and gravitational conditions in the early universe. Slightly denser regions later help form galaxies and clusters. Slightly thinner regions become the great voids between them. The pattern is therefore both a fossil of the early cosmos and a seed map of the structure that develops afterward. It also provides something less obvious, a ruler written into the sky. In the hot plasma, before light moves freely, gravity tries to compress over-dense regions while radiation pressure pushes outward. The result is a series of acoustic oscillations, waves of compression and rarefaction moving through the early cosmic material. These waves do not create sound that can travel through present-day space, but they follow related physics. A disturbance begins in a dense region and propagates outward through the plasma at a known fraction of the speed of light. By the time the universe becomes transparent, the wave has reached a characteristic maximum distance from its origin. That distance is known as the sound horizon. It provides a standard scale, because the physics of the early plasma determines how far the wave can travel before the photons decouple from matter. Cosmologists cannot place a physical ruler across that ancient surface, but they can predict the sound horizon from the measured contents and expansion of the early universe. They can then examine how large that known scale appears in the sky. This is where geometry enters. An object of known size appears under a certain angle, depending on its distance and on the curvature of the space through which its light travels. In flat geometry, the relation between physical size, distance, and apparent angle follows the familiar rules of Euclidean mathematics. In positively curved space, light paths tend to converge, making a fixed ancient scale appear larger than it would in flat space. In negatively curved space, light paths tend to diverge, making the same scale appear smaller. The sound horizon therefore acts like one side of an enormous cosmic triangle. The other sides are the paths travelled by light from opposite ends of that ancient scale to an observer. Measuring the angle between those paths tests the geometry through which they cross. No wooden ruler stretches across the universe, and no external viewpoint is needed. The early universe creates a standard length, and ancient light carries its apparent width forward. The temperature variations in the microwave background contain repeated patterns at different angular scales. Cosmologists describe these patterns through an angular power spectrum, which shows how strongly temperature differences occur across broad or narrow separations in the sky. Peaks appear in this spectrum because the acoustic waves reach different stages of compression or expansion when the universe becomes transparent. The position of the first major peak is especially important for geometry. It corresponds roughly to the larger scale that completes a characteristic compression before last scattering. Its angular size reveals whether light paths have converged, remained geometrically neutral, or diverged during their long journey. When the observed peak appears near the position predicted for flat space, the evidence indicates that the observable universe has very little average spatial curvature. The measurement does not rely on one triangle drawn between three visible objects. It uses a statistical pattern spread across the entire microwave sky. Countless regions contribute, allowing local irregularities to be separated from the underlying large-scale geometry. Foreground emission from the Milky Way must be modelled and removed. Instrumental effects must be understood. Gravitational lensing by later structures slightly distorts the ancient pattern, yet after these corrections, the geometry encoded in the microwave background remains remarkably consistent with near flatness. The phrase near flatness is essential. Measurements always carry uncertainty, and exact flatness cannot be demonstrated with unlimited precision. A universe with an enormous radius of curvature could appear flat across the observable region in the same way that a small landscape appears flat on Earth. If the curvature scale lies far beyond the cosmic horizon, no available triangle would be large enough to reveal it. The microwave background therefore tests the geometry of the observable universe with extraordinary power. But it does not grant access to the full cosmos beyond the region from which light has had time to arrive. It can rule out strong curvature across the visible domain, while leaving open a slight curvature spread over a much larger whole. The triangle method also depends on a model of cosmic history. The sound horizon must be calculated from the behavior of matter, radiation, and expansion before last scattering. If some unknown early component alters the speed of the acoustic waves or the expansion rate, the inferred ruler could change. Cosmologists therefore combine microwave measurements with other evidence. The distribution of galaxies preserves a later version of the same acoustic scale, known through baryon acoustic oscillations. Exploding stars provide distance measurements across cosmic time. Gravitational lensing, galaxy clustering, and estimates of the expansion rate add further constraints. When different methods agree within their uncertainties, confidence grows that the apparent flatness is not an artifact of a single assumption. Even then, some combinations of parameters can imitate one another. Curvature, dark energy, matter density, and the expansion history can produce partially similar effects on observed distances. This is called a degeneracy, meaning that different cosmic models may fit one set of data almost equally well. Additional observations are needed to break the resemblance. The microwave background gives a powerful anchor because it reaches so far back, while lower redshift surveys trace how geometry and expansion behave later. Together they narrow the possibilities. The use of triangles across the universe is therefore more subtle than adding three angles with an enormous protractor. The triangle is built from predicted physical scales, observed angular separations, and light paths shaped by the expansion and curvature of space. Its vertices lie in regions separated by billions of years of cosmic history. One vertex is the observer, while the others belong to the distant last scattering surface. The sides are not rigid lines drawn through static space. They are routes followed by photons through an evolving space-time, yet the central principle remains the same as it is on a sphere, a saddle, or a plane. Geometry determines how angles relate to lengths. The universe can reveal its shape because light remembers the geometry it crosses. The earliest visible radiation is especially valuable because it travels through nearly the entire observable history. Small deviations in geometry accumulate over that vast distance, making the apparent scale sensitive to curvature. A slight convergence or divergence that would be undetectable nearby can become measurable across the depth of the cosmos. Ancient light turns distance into leverage. At the same time, the near uniformity of the microwave background raises another question. Regions separated by wide angles appear to have almost the same temperature, even though a simple expansion history suggests that they could not have exchanged signals before the light was released. This horizon problem helps motivate cosmic inflation, a proposed era of extremely rapid early expansion. Inflation can allow regions now far apart to originate from a smaller connected domain, and it can stretch any earlier curvature toward apparent flatness. The same background that measures geometry therefore hints at a process that may explain why the geometry is so close to flat. Yet that explanation belongs to a later stage of the mystery. For the moment, the microwave sky serves as a vast geometric record. Its tiny temperature variations preserve the dimensions of ancient pressure waves. Their apparent angular size shows how light paths behave across cosmic distance. The answer emerging from those triangles is not a dramatic curve closing visibly around the sky, nor an obvious saddle opening into darkness. It is something quieter and more demanding within the reach of observation. Space behaves almost exactly as though it were flat. The large-scale curvature of the universe is not chosen independently of what the universe contains. In the standard cosmological picture, geometry and energy density are linked. Matter, radiation, and other forms of energy do not merely occupy space after its shape has been decided. Their total contribution helps determine whether space is positively curved, flat, or negatively curved. This connection turns the question of cosmic shape into a question of accounting. How much energy exists? How is it distributed? And how does that amount compare with the rate at which the universe expands? The answer is expressed through a critical density, a special value that separates the three broad geometric possibilities. If the total density is greater than this critical value, positive curvature is favoured. If it is lower, negative curvature is favoured. If it matches the critical value, spatial geometry is flat. The word critical does not imply danger. It identifies the dividing line between different geometric regimes. The value itself depends on the expansion rate, because expansion and gravity are part of the same cosmic balance. A rapidly expanding universe requires a higher density to reach the flat condition than a slowly expanding one. Density alone is therefore not enough. It must be interpreted together with the rate at which cosmic distances are growing. This relation appears in the equations that describe a universe that is broadly uniform and the same in every direction. On small scales, the cosmos is not uniform. Galaxies gather in clusters, clusters form filaments, and vast voids separate the densest structures. Yet when the view is widened enough, these irregularities can be treated as fluctuations within an average background. Cosmology then uses that average to describe the expansion of space. The relevant equations connect the expansion rate with the energy density, pressure, and curvature of the universe. Curvature is not added as a decorative feature. It is one term in the cosmic energy balance. A flat universe corresponds to the case in which the measured expansion and the total energy density fit together exactly according to that relation. Any excess or shortage appears geometrically. Matter contributes in several forms. Ordinary matter includes atoms, gas, dust, stars, planets, and every visible structure built from familiar particles. It is only a small part of the total cosmic inventory. Dark matter contributes far more mass than visible matter, although it does not emit or absorb light in ordinary ways. Its presence is inferred from gravitational effects, including the motions of galaxies, the behavior of clusters, gravitational lensing, and the growth of large-scale structure. Radiation also contributes, especially in the early universe, when photons and other relativistic particles carry a significant share of the total energy. As the universe expands, the density of matter and radiation change differently. Matter becomes diluted because the same amount occupies a larger volume. Radiation is diluted in the same way, but its wavelength is also stretched, reducing the energy of each photon. Radiation therefore fades more rapidly than matter as the universe grows. A further component complicates the balance. Dark energy is the name given to whatever drives the observed acceleration of cosmic expansion. In the simplest model, it behaves like a constant energy density associated with empty space, unlike matter, which thins as volume increases. This form of energy remains at roughly the same density while more space appears. Its total contribution can therefore grow as the universe expands. Dark energy also carries negative pressure in the equations of cosmology, and that pressure affects the expansion of space-time. It does not curve space in the same way as a pile of ordinary mass placed in one region. Instead, it alters the large-scale evolution of the universe. The total density relevant to cosmic geometry includes all these components together. Visible matter alone cannot settle the question. Dark matter, radiation, dark energy, and any additional fields must also be counted. To make the comparison easier, cosmologists define a density parameter. It is the actual total density divided by the critical density. When this ratio is greater than 1, positive curvature is associated with the model. When it's less than 1, negative curvature is associated with it. When it equals 1, the geometry is flat. Each component can receive its own density parameter, and the sum indicates how the total inventory compares with the critical value. Curvature can also be expressed as a related parameter, showing how far the universe departs from flatness. These are compact mathematical tools, but their physical meaning is simple. The cosmic contents are being weighed against the expansion. An older intuition compares this balance with the motion of an object thrown upward. Too little speed allows gravity to reverse the motion. Enough speed permits escape. A speed precisely at the threshold lies between the two outcomes. This analogy once encouraged a direct association between positive curvature and eventual collapse, flatness and endless slowing, or negative curvature and eternal expansion. Modern cosmology shows that the situation is more subtle. Geometry and fate are not identical. Dark energy can cause a positively curved universe to expand forever, while other forms of energy could alter the future behavior of a flat or negatively curved universe. Curvature describes spatial geometry. Cosmic fate depends on the full evolution of all energy components and their pressures. The density balance remains crucial, but it does not reduce the future to one simple rule. The reason the critical density is so striking is that it is extremely low by everyday standards. Spread across enormous volumes, only a very small average mass equivalent is required. The reference picture of a few hydrogen atoms within a cubic meter captures this sparseness, though the true inventory cannot be represented as hydrogen alone. Most cosmic energy is not in ordinary atoms, and much of the universe is contained in forms that do not gather into visible objects. The analogy still reveals the scale of the balance. A universe can be almost empty by local experience, and yet possess enough total energy density to determine its global geometry. Measurements of the density come from many directions. Galaxy motions and gravitational lensing help estimate matter. The cosmic microwave background constrains the early balance and the geometry through the acoustic pattern. The abundance of light elements records conditions during the first stages of nuclear formation. Surveys of galaxies reveal how structure grows and how the expansion rate changes. Exploding stars act as distance indicators, helping trace the acceleration of the universe. No single observation provides the entire inventory. The result emerges from combining evidence that spans different eras and physical processes. This combination is necessary because the components can imitate one another in limited datasets. A change in curvature can alter observed distances. A change in dark energy can also alter those distances. Matter density affects both expansion and the growth of structure. The initial pattern of fluctuations changes how later galaxies appear. Cosmologists therefore seek measurements with different sensitivities. The microwave background reaches the early universe. Galaxy surveys test later structure. Lensing maps the integrated gravitational effect along the line of sight. When the same model survives all these tests, its parameters become tightly constrained. The deepest puzzle is not simply that the present density lies close to the critical value. It is that any small departure from the flat condition in the early universe should generally grow more important as cosmic history unfolds, unless some mechanism suppresses it. if the early density had been even slightly away from the critical value. The later universe might have become strongly curved. The current near flatness therefore suggests that the initial balance is extraordinarily precise, or that an early process drives the geometry toward flatness. This is the flatness problem. It is not a claim that exact flatness has been proven. It is a question about why the observable universe is so close to the dividing line. Inflation offers one possible answer by proposing a brief period of accelerated expansion in the early universe. Such expansion can stretch a curved region until it appears nearly flat, much as a tiny patch on an enormous sphere appears level. Inflation does not remove every mystery, and its detailed mechanism remains uncertain. But it transforms near flatness from an unexplained coincidence into a possible consequence of cosmic history. Before that explanation is considered fully, the density relation establishes the central fact: the geometry of the universe is written into its contents. Matter, radiation, dark matter, dark energy, expansion, and curvature participate in one connected balance. The shape of space is therefore not an isolated property hidden behind the stars. It is the large-scale expression of everything the universe contains and of how rapidly the distance between its regions changes. The measurements do not reveal space closing tightly upon itself or opening strongly with distance. Instead, every major line of evidence points toward a quieter result. Across the observable universe, the average spatial geometry appears extremely close to flat. This does not mean that every region is free of curvature. Stars, galaxies, clusters, and black holes still deform spacetime locally. It means that when those distortions are smoothed over the largest available scales, the remaining background behaves almost exactly like flat geometry. Parallel paths remain nearly parallel. Cosmic triangles have nearly the expected angular sum, and the relation between distance and apparent size closely follows the flat case. Measurement can approach zero curvature, but it cannot confirm zero with infinite precision. A universe with a very large radius of curvature could look flat throughout the observable region, just as a small patch of an enormous sphere looks level. The evidence therefore describes what can be seen, not necessarily the total structure beyond the horizon. The strongest constraint comes from combining different observations rather than trusting a single cosmic ruler. The microwave background provides the most distant geometric test. Its acoustic pattern contains a preferred scale, established by pressure waves in the early plasma. That scale appears in the sky at almost exactly the angular size expected in a flat universe. If space had strong positive curvature, the pattern would appear wider. If space had strong negative curvature, it would appear narrower. The observed position of the main acoustic features lies close to the flat prediction. Yet this measurement alone cannot fully separate curvature from the effects of other cosmic parameters. A different expansion history can change the apparent distance to the last scattering surface, dark energy, matter density, and the present expansion rate can partly imitate changes in geometry. The microwave background therefore provides a powerful foundation, but not a complete answer by itself. Later cosmic structures add new pieces. The same early pressure waves that shape the microwave background leave a faint preferred spacing in the distribution of galaxies. This pattern, known as baryon acoustic oscillation, serves as a standard ruler across more recent cosmic time. Galaxy surveys measure its apparent size along and across the line of sight. Those measurements reveal both how distances grow with redshift and how quickly the universe expands at different eras. A curved universe changes these relations in a predictable way. When the galaxy ruler is combined with the ancient ruler in the microwave background, many of the possible imitations begin to fail. Exploding stars contribute another distance scale. certain stellar explosions have similar intrinsic brightness, allowing cosmologists to estimate how far away they are by comparing their expected and observed light. Their fading pattern shows that cosmic expansion accelerates at late times, a result associated with dark energy. This expansion history influences how curvature is inferred, so the supernova measurements help separate one effect from another. Gravitational lensing offers still another test. Light from distant galaxies is bent by the matter it passes, producing slight distortions in their apparent shapes. When millions of galaxies are measured statistically, the distortions trace both the distribution of mass and the geometry of the paths between source, lens, and observer. Lensing is sensitive to dark matter, cosmic structure, and the expansion of space. It therefore checks whether the same nearly flat model that fits ancient radiation and galaxy spacing also fits the accumulated bending of light. Near flatness survives because many parts of the cosmic record converge on it. The numerical result is often expressed through the curvature density parameter, which would be 0 in an exactly flat universe. Observations place this parameter very close to 0, with an uncertainty small enough to rule out strong curvature across the observable domain. The precise limit depends on which data sets and assumptions are used, so a single fixed percentage can become misleading when repeated without context. Some analyses permit a small positive or negative curvature. Others narrow the range further when additional observations are included. What remains stable is the broad conclusion any cosmic curvature must be slight on the scales currently accessible. The radius associated with that curvature, if it exists, would be much larger than the observable region. The visible universe would then occupy only a small patch of a much broader geometry. This result can sound disappointing because flatness seems ordinary. A closed universe appears more exotic, offering the possibility that a journey continued long enough might return to its starting point. A negatively curved universe seems equally strange, with distances opening faster than flat intuition allows. Flat space appears familiar by comparison, yet its familiarity is deceptive. Flatness is not the absence of a question. It is a precise geometric condition. The total density of energy and matter must match the critical density associated with the expansion rate. Too much would favour positive curvature. Too little would favour negative curvature. The universe seems to lie extraordinarily close to the dividing line. That closeness demands explanation. The difficulty becomes sharper when cosmic history is considered. In many simple expanding models, a small early departure from flatness grows more important over time. A universe that begins slightly above the critical density tends to move farther toward positive curvature. A universe that begins slightly below tends to move farther toward negative curvature. For the present universe to remain so close to flat, the early balance must therefore have been extremely precise. The farther back the calculation is carried, the more exact that balance appears to require. It is a sign that the basic model may be missing an early process that drives the universe toward flatness. The problem is not that flat geometry is mathematically forbidden. It is that flatness seems unstable under ordinary expansion, unless the initial conditions are tuned with extraordinary care. The early universe may solve this through inflation, a proposed period of accelerated expansion. If a small region of space expands by an enormous factor, any pre-existing curvature becomes stretched across a much larger scale. A curved surface viewed over a tiny patch appears flat, and inflation applies a related idea to cosmic geometry. The observable universe could emerge from one small part of a far larger inflated region, leaving this local geometry almost perfectly flat even if the total structure retains some curvature beyond reach. Inflation also helps explain the uniform temperature of widely separated regions in the microwave background, and provides a mechanism for generating the small primordial fluctuations that later grow into galaxies. Yet the exact physics driving inflation remains uncertain, and different models make different predictions. Near flatness is consistent with inflation, but it does not identify one unique inflationary mechanism. Another possibility is that exact flatness is built into the deeper structure of the universe in a way not yet understood. The total energy density may be constrained by a principle beyond the present model. Quantum gravity may alter the meaning of curvature near the beginning. The universe may pass through an earlier phase in which the familiar balance between density and expansion does not apply. These possibilities remain speculative because no confirmed theory describes every stage. The observations support near flatness. They do not reveal why it occurs. Even the phrase observable universe imposes a hard boundary. Light has travelled for a finite cosmic time, and expansion limits which regions can send signals to the present. Measurements therefore cover only a finite volume. If the entire universe is vastly larger, its average curvature could differ slightly from the local value. Large-scale variations might exist beyond the horizon. The observable region could be unusually flat compared with the whole, though the simplest cosmological models assume broad uniformity. That assumption is supported within the visible domain, but it cannot be tested everywhere. No telescope can compare the local geometry with regions from which no signal arrives. Near flatness therefore stands as both an answer and an opening. It answers the practical geometric question. Within the observable cosmos, space shows no strong average curvature. It rejects a tightly closed universe and a strongly open one across the region that can be measured. Yet it leaves several deeper questions untouched. It does not prove that space is infinite. It does not determine how distant regions connect. It does not reveal whether a tiny curvature becomes apparent far beyond the horizon. Most of all, it does not explain why the cosmic density lies so close to the critical value. The universe appears balanced on the boundary between two curved possibilities, and the balance is so exact that apparent simplicity becomes one of the largest mysteries in cosmology. Flatness seems to offer an immediate answer to the question of cosmic extent. A flat surface is easy to picture as an endless plane, spreading without boundary in every direction. If the large-scale geometry of space follows the same rules, it is tempting to conclude that the universe must also continue forever, yet the conclusion does not follow. Flatness describes how distances, angles, and parallel paths behave. Infinity describes how much space exists. These are related ideas, but they are not identical. A universe can be flat and infinite, but it can also be flat and finite if its regions are connected in the right way. The measurements showing near flatness therefore settle only part of the problem. They reveal the local and observable rules of geometry while leaving the total size of the cosmos uncertain. The simplest flat model is indeed infinite. In that picture, space extends without edge, without return, and without a final boundary. A journey continued in one direction never reaches an end and never circles back. New regions always lie ahead. The total volume is unlimited, and every observable patch belongs to a larger expanse that continues beyond the cosmic horizon. This model is mathematically natural because ordinary Euclidean space has exactly these properties. It also fits the observed near flatness without requiring any special global identifications. For that reason, an infinite flat universe often becomes the default image in discussions of cosmology. Yet simplicity is not proof. Observations test only a finite region, and geometry measured inside that region cannot determine whether the same space continues without limit or eventually reconnects with itself. The difference becomes clearer through topology. Geometry describes the rules of measurement within a space. Topology describes how the space is connected as a whole. Two spaces can share the same local geometry while possessing different global structures. A flat sheet and the surface of a cylinder provide a simple analogy. A small creature living on either surface can measure parallel lines and flat triangles and obtain the same local results. Yet the sheet extends openly in two directions, while the cylinder closes around one direction. A traveller moving around the cylinder eventually returns to the starting point without crossing an edge. The surface remains locally flat because it can be unrolled into a plane without stretching. Its global connection, not its local curvature, creates the return. A cylinder still extends without limit along its length, so it is only partly finite. A more complete analogy joins both pairs of opposite edges on a flat rectangle. The result is commonly represented as a torus, though the familiar donut shape is only an embedding used for visualization. A true flat torus does not need to curve through an external space. From within, every small region can remain perfectly flat. A traveller crossing one boundary re-enters through the opposite boundary, and repeated travel in a fixed direction eventually returns to the starting point. The total area is finite, yet there is no edge. In 3 dimensions, an analogous structure can be built by connecting opposite faces of a flat volume. Movement through one face continues through the matching face, producing a finite space with no boundary. Such a universe would be flat in geometry, but compact in topology. It would contain a limited total volume even though no location marked an end. This possibility changes the meaning of infinity. Space may feel endless to any local observer, because no wall appears, yet it may contain only a finite set of regions arranged through repeating connections. The same galaxies could, in principle, be seen along different paths. Light leaving a distant object in one direction might travel around the universe and approach from another. A single galaxy cluster could produce several images at different positions in the sky, each showing the object at a different stage of its history, because the light paths have different lengths. The cosmic microwave background might also contain repeated patterns, with matching circles or correlated regions created when the last scattering surface intersects itself through the global topology. Searches for such signatures attempt to determine whether the observable universe wraps around on scales small enough to detect. So far, no convincing repeating pattern has established a compact flat topology within the visible domain. This absence places lower limits on the size of any repeating cosmic cell, but it does not prove that no such structure exists. If the fundamental region is larger than the observable universe, light has not had enough time to complete a circuit or reveal duplicated structures. A finite flat cosmos can therefore hide beyond the horizon just as effectively as an infinite one. The observable universe itself must not be confused with the entire universe. The observable region is finite because light has travelled for only a finite cosmic time, and because expansion affects which signals can reach the present. Its boundary is not a physical wall, it is a horizon set by causality. More distant regions may exist beyond it, but their light has not arrived, and may never arrive if accelerated expansion continues. The observable universe can therefore be finite even when the total universe is infinite. Conversely, the total universe could be finite while still being much larger than the observable region. The horizon tells how far information has reached, not how far space extends. This distinction is essential because many images of the cosmos show a glowing sphere with a defined outer surface. That sphere represents the visible limit around an observer, not an edge of creation. Another observer in a distant galaxy would possess a different observable sphere centered on that location. The two regions might overlap, but neither would occupy a privileged cosmic center. In a broadly uniform universe, every observer sees an expanding horizon centered on the observer, even though the universe itself has no central point within space. The apparent centre belongs to the act of observation, not to the geometry of the whole. A flat, infinite universe would contain infinitely many regions beyond the horizon, perhaps with an unlimited amount of matter if the average density remains positive. This possibility leads to questions that exceed direct observation. In an infinite space with broadly similar physical conditions, rare arrangements might occur repeatedly at sufficiently great distances, yet such conclusions depend on assumptions about uniformity, quantum states, and the distribution of matter far beyond the visible domain. Near flatness alone does not establish them. It does not prove infinite repetition, an unlimited number of galaxies, or exact copies of local history. Those ideas require additional premises that cannot currently be tested across the entire cosmos. A finite flat universe raises different mysteries. Its topology would introduce preferred connection scales, even if its local geometry remained uniform. Some directions might wrap around more quickly than others. The repeating cell could be cubic, elongated, twisted, or connected through more complex transformations. Light paths could return with reversed orientation or shifted position depending on the topology. The universe would have no edge, but it would carry a hidden global pattern. Detecting that pattern would require observations extending across a substantial fraction of its total size. If the compact dimensions were only slightly larger than the visible horizon, subtle correlations might remain in the microwave background or in the distribution of distant objects. If they were vastly larger, the cosmos would be observationally indistinguishable from an infinite flat universe. This indistinguishability is not merely a limitation of current telescopes, it may be a permanent boundary. Accelerated expansion can carry distant regions away so rapidly that signals emitted there never reach the observer. Even as instruments improve, the accessible portion of the universe may not grow enough to reveal the global topology. The answer to whether space is truly infinite could remain hidden, not because the question lacks meaning, but because the necessary evidence lies outside every possible exchange of information. Cosmology can then constrain possibilities without selecting one final structure. It can say that observable space is close to flat, that no small repeating topology has been securely detected, and that any curvature radius or compact scale must exceed certain observable limits. It cannot transform those limits into proof of infinity. The deeper lesson is that shape, size, and connectedness form separate layers of description. Curvature answers how geometry behaves, topology answers how regions join, extent answers whether the total volume is finite or infinite. A complete portrait of the universe requires all three, yet present observations speak most clearly only about the first. Space appears flat within the visible domain. It may continue forever in the simplest possible way. It may also close through connections too large to reveal themselves. Near flatness narrows the field, but it does not end the search. The universe can obey the geometry of an endless plane while concealing a finite architecture beyond the reach of light. A universe can be finite without ending anywhere. The idea sounds contradictory only because ordinary experience links finiteness with boundaries. A room is finite because walls enclose it. An island is finite because water surrounds it. A page is finite because its edges can be reached. Space itself does not have to follow that pattern. Its total volume can be limited while every direction continues smoothly, with no wall, rim, or final surface. The clearest analogy remains the surface of Earth. It has a finite area, yet a traveller moving across it never encounters an edge of the surface. The route can continue until it eventually returns to its starting point. A closed cosmic space would extend this principle into 3 dimensions. The universe would not be contained inside some larger emptiness. Its finiteness would arise from the way space connects to itself. This is a question of topology, the branch of mathematics concerned with continuity and connection. Geometry measures curvature, angle, and distance. Topology asks which paths can be continuously transformed into one another, and whether distant regions are secretly the same region joined through a larger structure. Two universes can possess the same local geometry, and still differ globally because their connections are different. A small observer may notice no difference at all. Every nearby triangle can look flat, every short light path can behave normally, and every local law of physics can remain unchanged. Only journeys or signals crossing a substantial fraction of the whole cosmos reveal the hidden pattern. In one simple finite model, opposite faces of a vast region are identified. Crossing one face does not pass through a barrier. The traveller simply continues through the corresponding face on the other side. Nothing special need occur at the connection, because the boundaries are not physical surfaces. They're only a way of describing the repeated geometry. The same construction can be applied in several directions, producing a universe with finite volume and no edge. It is often imagined as a three-dimensional torus, though the name can mislead when it suggests an ordinary donut floating in a surrounding room. The actual space does not need to bend into an external dimension. From within, it can remain flat everywhere. Its compactness comes from identification rather than curvature. A straight path can therefore close into a loop even while the geometry along that path remains flat. A beam of light leaving a galaxy may cross the entire universe, return from another direction, and continue past the same region again. If the cosmos is small enough, one object can appear several times in the sky. Each image would be created by light taking a different global route. One path might be relatively short, another might wrap around the universe before reaching the observer. The images would not necessarily look identical because they would show the object at different ages. A galaxy seen along the shorter path might appear more evolved, while a longer path could reveal the same galaxy at an earlier stage. Orientation could also change if the topology includes a twist or reflection. The repeated object might appear rotated, mirrored, or distorted by structures encountered along the way. Detecting such repetitions is difficult because the universe changes while light travels. Galaxies merge, stars form, dust shifts, and large-scale structures evolve. Two images of the same object separated by billions of years of light travel may look so different that their common identity becomes hidden. Motion and gravitational lensing complicate the comparison further. A simple search for identical pictures would therefore miss many possible signatures. Cosmologists instead examine statistical patterns that should survive the long journey. The cosmic microwave background is especially valuable because its ancient surface surrounds every observer and carries a nearly global pattern. In a compact universe, the same region of that surface might be visible along more than one direction. This could create matching circles in the microwave sky. The temperature variations along one circle would correspond to variations along another because both trace the same physical region seen through different paths. The circles could have different orientations depending on the topology. Their existence would provide a powerful sign that space wraps around within the observable range. Searchers have not found a universally accepted pattern of this kind. That absence suggests that any compact dimensions are larger than the portion of space easily tested, or that the topology produces signatures more subtle than the simplest searchers can detect. It does not eliminate finite space. A universe whose repeating scale exceeds the observable diameter would show no duplicated regions at all. The visible cosmos would then resemble a small patch cut from a much larger closed structure. Every measurement inside the patch could remain consistent with ordinary infinite space. This is the central difficulty. Global topology becomes observable only when light has enough time to explore the global connections. If the shortest loop through space is longer than the maximum distance from which signals have arrived, no observation can complete the circuit. The universe may be compact, but its compactness would lie beyond the horizon. Even a finite cosmos can therefore appear endless. There are many possible compact topologies. Some identify opposite faces directly. Others connect them after a rotation. Some allow paths to return with reversed orientation. Positive curvature supports its own family of closed spaces, including structures related to a higher dimensional sphere. Negative curvature can also form finite volumes through more complicated identifications, even though negatively curved space naturally expands rapidly with distance. The familiar labels closed, flat, and open are therefore not complete descriptions. A positively curved space is often finite, but its precise topology can vary. A flat space may be infinite or compact. A negatively curved space may also be finite under certain global constructions. Curvature limits the possibilities, yet it does not choose a unique cosmic architecture. The absence of an edge also removes the need for a center. On the surface of Earth, no location is the center of the surface itself. A center can be defined only by stepping into the surrounding three-dimensional space and pointing toward Earth's interior. But that interior is not part of the surface geometry. A closed universe likewise need not contain a central point within space. Every galaxy can observe distant galaxies receding on large scales, and no galaxy occupies a privileged origin. The expansion is not matter flying away from one location into a pre-existing void. It is an increase in the distances measured through the geometry. In a finite closed space, the total volume can grow while the topology remains unchanged. The cosmic connections persist as every large-scale length expands. A loop around the universe becomes longer, but it remains a loop. This allows a finite universe to expand without expanding into anything. The question of what lies outside loses its ordinary meaning because outside is not a direction contained in the geometry. The universe is not a balloon filled with galaxies on its surface in a literal surrounding room. The balloon analogy is useful only because the surface can grow while having no edge. The external air and interior volume belong to the analogy, not necessarily to physical reality. A three-dimensional universe can change its scale through time without requiring an extra spatial place to receive it. This distinction becomes essential when finite space is discussed, because ordinary language repeatedly tries to place a boundary around it. Yet a boundary is precisely what a compact universe does not need. Every point has neighboring points in every direction. Every local path can continue. Finiteness appears only when the full set of connections is traced. The cosmos may therefore conceal its total size behind perfect continuity. No signpost marks the completion of a circuit. No seam divides one copy of space from another. If light returns, it does so through ordinary geometry, carrying an image that may be mistaken for a separate object. If matter travels around the universe, it crosses no special threshold. The hidden structure is not a wall but a pattern of identity. Distant regions that seem separate may be one region approached along different routes. Present observations have not revealed such a pattern with confidence. They place limits on the smallest possible compact scale and show that the observable universe does not obviously repeat in a simple way. Beyond those limits, the possibilities remain open. Space may be infinite, offering endlessly new regions. It may be finite and vastly larger than the horizon. It may possess a complex topology whose repeating signals are too faint or too distorted to identify. The most unsettling possibility is not that the universe ends, but that it never ends locally even while containing only a finite whole. Its paths continue, its horizons shift, and its geometry remains smooth. while the same cosmic volume closes silently upon itself. The observable universe is not the whole universe. It is the region from which signals have had enough time to reach the present, shaped by both the finite age of the cosmos and the history of expansion. This boundary is not a wall, a shell of matter, or the outer surface of creation. It is a horizon set by causality. Beyond it, space may continue, but no light from those regions has yet arrived. Some regions may remain unreachable forever if accelerated expansion carries them away faster than signals can close the growing distance. The horizon therefore marks the limit of available evidence, not necessarily the limit of existence. Every attempt to determine whether space is infinite, finite, flat, curved, or connected through a hidden topology must confront this boundary. The universe can be measured only from inside one visible domain, and the domain itself may represent a very small fraction of the total cosmos. The oldest electromagnetic radiation comes from the cosmic microwave background, released when the universe becomes transparent. It forms a distant spherical surface around the observer, but that surface does not mark the edge of space. It marks the earliest time from which ordinary light can travel freely. Earlier than that, the plasma is opaque, scattering photons too frequently for a direct image to survive. Other messengers may carry information from earlier stages. Gravitational waves could, in principle, preserve traces from epochs hidden to light. Neutrinos also decouple earlier than photons, though detecting the ancient neutrino background remains extraordinarily difficult. Even these messengers would still belong to the causal structure of the observable universe. They might look deeper into cosmic history, but they would not reveal regions forever outside contact. The visible horizon is also larger than a simple estimate based on the age of the universe multiplied by the speed of light. While light travels, space expands. A photon emitted long ago crosses distances that change during its journey. The matter that released the oldest observable light is now much farther away than the travel time alone might suggest. Cosmologists therefore distinguish several horizons and distance measures, each suited to a different question. The particle horizon describes the maximum region from which information could have reached the observer since the beginning of the hot expanding phase. The event horizon describes the boundary beyond which events occurring now will never send signals that reach the observer, assuming the future expansion follows the current accelerated trend. The Hubble radius marks a scale related to the present expansion rate, but it is not itself a permanent wall. Galaxies can lie beyond that radius and still be visible, because their light begins its journey under earlier conditions, and because the relation between recession and signal travel changes through time. These distinctions show why the edge of observability is not a single simple sphere frozen in space. It is part of an evolving space-time. Every observer possesses an observable universe centered on the observer. A galaxy billions of light-years away has its own horizon, overlapping with the local one but extending into regions that cannot be seen from Earth. This does not make either galaxy a center of the entire cosmos. The apparent center arises because observation spreads outward from a particular location. In a broadly uniform universe, the same pattern holds everywhere. Each observer receives ancient light from a surrounding sphere and sees distant galaxies receding on large scales. Expansion has no confirmed central point within space. It is the geometry between widely separated regions that changes. The horizon is therefore personal in position but universal in principle. It follows every world without identifying any world as privileged. This has a severe consequence for the question of global shape. Suppose the total universe is a positively curved closed space, with a radius far larger than the observable region. Every accessible measurement could still indicate near flatness. The local patch would be too small to reveal the closure. Suppose instead that space is flat but compact, repeating only after a journey longer than the observable diameter. No duplicated galaxies or matching microwave patterns would appear. Suppose space is truly infinite. The observable data could look exactly the same. These three universes may differ profoundly in total extent and topology, while remaining observationally indistinguishable inside one horizon. Better instruments can reduce uncertainty within the visible region, but they cannot automatically reach beyond causal limits. The problem is not only technological, it is built into space-time. Cosmologists try to stretch the available evidence as far as possible. The cosmic microwave background tests geometry across the deepest visible distance. Galaxy surveys map structures over enormous volumes and search for repeating arrangements. Standard rulers and standard candles trace the relation between distance and expansion. Gravitational lensing measures how matter and geometry distort light along long paths. Statistical tests examine whether the universe appears homogeneous and isotropic, meaning broadly uniform and directionally similar when viewed on the larger scales. These methods can show that observable space lacks strong curvature and does not repeat on scales smaller than certain limits. They can constrain the minimum size of a closed or compact universe. They cannot prove that no closure exists farther away. A lower bound can grow without becoming infinity. The observable horizon also hides possible large-scale variations. Standard cosmology assumes that the universe beyond the visible region resembles the universe within it when averaged over great distances. This cosmological principle is supported by the broad uniformity of the microwave background and the distribution of matter across surveyed scales. Yet it remains an extrapolation when applied to regions that no signal can reach. Beyond the horizon, the density could in principle vary, the curvature could change gradually, or the topology could connect in ways that leave no local trace. Inflation often predicts a universe vastly larger than the observable patch and can produce regions with different conditions in some models. Such possibilities are not confirmed descriptions of reality. They reveal how much can remain undecided once observation reaches its causal edge. The horizon also changes with cosmic time. As the universe ages, light from previously unseen regions may arrive, enlarging the particle horizon, yet accelerated expansion creates a competing effect. Distant galaxies cross beyond practical reach, as the light they emit becomes increasingly redshifted and faint. Their future signals may never arrive. Over extremely long times, galaxies outside the local gravitationally bound region could fade from view, leaving future observers with a far smaller visible cosmos. The total universe would not necessarily shrink, but the accessible evidence would. Cosmic history can erase its own larger context. The current era may therefore offer an unusually rich view, with ancient radiation still detectable and many distant structures still visible. Even now, however, the horizon prevents a complete survey of space. The limitation reaches into questions of probability and repetition. In an infinite universe with sufficiently uniform conditions, extremely rare arrangements might recur at immense distances. In a finite universe, the total number of regions and possible structures could be limited, yet no observation can count what lies beyond the horizon. Arguments about repetition depend on assumptions concerning infinity, physical states, and the distribution of matter. The visible patch alone cannot establish them. It contains a finite amount of accessible information, even if the whole cosmos contains infinitely more. The horizon therefore separates empirical cosmology from broader inference. Within it, measurements can be compared, models tested, and uncertainties narrowed. Beyond it, conclusions become increasingly dependent on principles assumed to continue where direct evidence ends. This does not make the larger questions meaningless. It defines the level of confidence they can carry. The universe may leave indirect traces of its global structure inside the horizon. A compact topology might create repeated microwave patterns. A broad curvature might alter angular distances. An early inflationary phase might imprint specific correlations in primordial fluctuations. Cosmologists search for such signals because global properties can sometimes influence local observations. Yet the absence of a signal may have several meanings. The feature may not exist, it may be too weak, or its characteristic scale may exceed the visible domain. Silence beyond the horizon is not proof of emptiness or infinity. It is simply the absence of contact. The observable universe is therefore both a vast achievement of measurement and a narrow window. It contains billions of galaxies, ancient radiation, expanding distances, and enough history to reconstruct much of cosmic evolution. Still, it may be only one small patch of a far greater whole. Its near flatness describes the geometry inside the window. Its lack of obvious repetition constrains topology inside the window. Neither result determines what the full universe does beyond the reach of light. The final shape may be written across scales too large for any observer to survey, leaving cosmology with a precise map of the visible and a permanent uncertainty about the whole. Near flatness may be less a coincidence than a fossil of an earlier transformation. In the standard account of cosmic history, the universe expands from a hot, dense state, cools, forms particles and atoms, and eventually develops stars, galaxies, and the large-scale web of matter. Yet that familiar sequence may not begin with the ordinary expansion seen later. Many cosmological models place a brief and extraordinary phase before the hot universe settles into its more measured growth. This proposed phase is called inflation. During inflation, space expands at an accelerating rate, increasing its scale by an immense factor in a tiny interval. The expansion is not an explosion of matter into surrounding emptiness. It is the rapid stretching of geometry itself. Regions once close together become separated by distances far greater than light could cross during the same period. Any pre-existing curvature is carried outward and diluted across the expanding domain. The result is a universe that appears almost perfectly flat within the region later accessible to observation. The simplest analogy is the surface of a sphere. A small patch on an ordinary globe reveals its curvature when measured carefully. If the sphere is enlarged enormously while the patch is stretched with it, the same region becomes increasingly level. The curvature has not necessarily vanished from the entire sphere. Its radius has become so large that the patch looks flat. Inflation applies a related idea to three-dimensional space. A region that begins with positive or negative curvature can be expanded so dramatically that its local curvature becomes extremely difficult to detect. The observable universe may then occupy only a tiny part of a much larger inflated region. Within that patch, triangles behave almost as they would in flat geometry. Parallel paths show almost no global convergence or divergence, and the density lies very close to the critical value. Inflation does not require the total universe to be exactly flat or infinite. It predicts that any curvature visible before the accelerated expansion becomes stretched beyond the scales most likely to be observed. This directly addresses the flatness problem. Without inflation, a universe that remains close to the critical density for billions of years appears to require an extraordinarily precise beginning. A slight early excess in density tends to become associated with increasing positive curvature, while a slight shortage tends toward increasing negative curvature. The present near balance therefore implies an even more exact balance in the early universe. Inflation changes that behavior. During accelerated expansion, the curvature contribution becomes less important compared with the energy driving inflation. The density is pushed toward the critical value, not because matter is carefully adjusted atom by atom, but because expansion changes the relative importance of curvature. A wide range of initial conditions can then evolve toward a state that looks flat. The precision observed today becomes a consequence of dynamics rather than a mysterious initial tuning. Inflation also addresses another problem hidden in the cosmic microwave background. The ancient radiation has almost the same temperature in regions separated by enormous angles. In the simplest non-inflationary history, some of those regions appear too far apart to have exchanged light or heat before the radiation is released. Inflation proposes that they begin much closer together, within a smaller domain where physical interactions establish similar conditions. Rapid expansion then carries them far apart. The uniform sky and the flat geometry therefore emerge from the same basic event. A small connected region becomes enormously stretched. The process cannot be driven by ordinary matter alone. Matter and radiation usually slow cosmic expansion through their gravitational influence. Inflation requires a form of energy with unusual pressure, capable of producing accelerated growth. Many models describe it through a field, often called the inflaton. If this field occupies a suitable high-energy state, its energy density can remain nearly constant while space expands. Eventually the field changes state, inflation ends, and its energy is transferred into particles and radiation. This transition, called reheating, creates the hot conditions from which the later standard cosmic history proceeds. No confirmed inflaton particle has been detected, and the exact identity of the field remains unknown. Many mathematical models can produce accelerated expansion, differing in duration, energy scale, and predicted fluctuations. Inflation is therefore not one complete theory, but a broad family of scenarios. Their shared feature is early accelerated expansion. This flexibility allows inflation to fit several observations, but it also makes the idea difficult to test as one unique proposal. A scientific explanation must do more than reproduce known facts. It must make predictions narrow enough for some versions to fail. One major prediction concerns tiny quantum fluctuations. Even in an apparently empty state, quantum fields do not remain perfectly still. During inflation, microscopic variations are stretched to astronomical scales. After inflation ends, slightly denser regions attract more matter, while thinner regions become increasingly empty. Over immense time, these variations grow into galaxies, clusters, filaments, and voids. The temperature pattern in the microwave background preserves an earlier imprint of the same process. Its fluctuations are nearly scale invariant, meaning that their strength changes only slightly across a wide range of sizes, and they are close to a simple statistical distribution. These properties agree with many inflationary models, though they are not exclusive proof. Inflation may also produce primordial gravitational waves, ripples in space-time generated during the accelerated phase. Such waves could leave a distinctive twisting pattern in the polarization of the microwave background. Detecting that signal would reveal information about inflation's energy scale and could eliminate many competing models. The search is difficult because later gravitational lensing and foreground radiation from the Milky Way can imitate or obscure the pattern. No accepted detection has yet established primordial gravitational waves from inflation. Their absence at present sensitivity already constrains models that predict a stronger signal. Inflation remains supported by the combined consistency of several clues rather than by one decisive signature. The duration of inflation is uncertain, but it must be long enough to stretch curvature and connect the regions visible today. Repeated expansion can enlarge a microscopic domain until it contains the entire observable universe. If the process lasts longer, the total inflated region can become vastly larger than the visible cosmos. Some models allow inflation to end in certain regions while continuing elsewhere, producing eternal inflation and many separated domains. Such ideas extend beyond what present observations can confirm. They arise from particular versions of the mechanism, not from near flatness alone. Inflation, therefore, solves the flatness problem only at one level. It explains how curvature can be driven beyond observation, but it raises new questions about the origin and nature of the energy responsible. Why does the field begin in the required state? What determines its behavior? How does inflation start? And why does it end in a way that produces the observed particles and fluctuations? Does it occur once, or continue across regions indefinitely? These questions do not erase its explanatory power, but they show that one mystery has moved into a deeper layer. Alternative ideas attempt to explain near flatness without conventional inflation. Some propose a contracting phase before expansion, allowing the universe to smooth itself before a bounce. Others modify gravity or introduce different early cosmic conditions. These models must still reproduce the successful predictions of the hot, expanding universe, including the microwave background, the abundance of light elements, and the later growth of structure. None has displaced inflation as the leading framework, but the competition identifies which observations can truly distinguish one history from another. The flat appearance of space is therefore not merely a static measurement. It may be evidence of an ancient process that reshapes the scale of the universe before ordinary cosmic history begins. Inflation turns flatness from an improbable balance into a natural outcome of rapid expansion. It links geometry with the uniform microwave sky and with the tiny seeds of galaxies. Yet it does not reveal whether the total universe is finite, infinite, or curved on scales beyond the inflated patch. Even if inflation is correct, measurements can only constrain the curvature of the region that becomes observable, not certify the geometry or extent of every region produced beyond it. It explains why the visible region looks flat while allowing the larger cosmos to remain hidden. The apparent simplicity of space may therefore be the result of an event so extreme that it removes its own geometric traces, leaving only a nearly level horizon and a pattern of faint fluctuations behind. The universe gives a remarkably clear answer to one question and refuses to answer the next. Within the region that can be observed, space behaves as though its average curvature is very close to zero. Ancient light carries a geometric ruler from the early plasma. Galaxies preserve a later echo of the same scale. Exploding stars, gravitational lensing, and the growth of structure trace the history of expansion. Together, these measurements leave little room for strong positive or negative curvature across the visible cosmos. Yet the same evidence cannot reveal whether all of space is infinite, whether it closes far beyond the horizon, or whether distant regions connect through a topology too large to detect. The result is not ignorance in place of knowledge. It is a precise boundary around what knowledge can presently reach. Observable space is nearly flat. The total universe remains geometrically open as a question. This boundary exists because every measurement is made from inside the universe. No observer can step outside space-time and inspect its outline. Shape must be inferred through internal behavior. Light rays act as paths. Acoustic patterns act as rulers. Matter supplies gravitational landmarks. Expansion provides a changing scale. These tools reveal how geometry works across immense distances, but they do not produce an external silhouette. The universe does not present itself as a sphere, a saddle, or a plane floating in a larger darkness. Those images are analogies for mathematical relationships. Positive curvature means that large-scale paths tend to converge. Negative curvature means that they tend to diverge. Flatness means that the familiar geometric balance holds. The actual cosmos can obey one of these rules without resembling any everyday object. Even the statement that space is nearly flat contains an unavoidable qualification. A small patch of a vast curved surface looks flat, if the radius of cosmic curvature is enormously larger than the observable universe. Every available test can return a value extremely close to zero. The curvature may exist, but its effect may be spread so gently that no visible triangle is large enough to expose it. Measurements can push the minimum curvature scale farther outward. They can rule out a tightly closed cosmos and a strongly open one. They cannot transform a finite uncertainty into absolute proof. Exact flatness is a mathematical possibility. Slight positive curvature remains a possibility. Slight negative curvature remains a possibility. The visible domain may lie near the center of the allowed range, while the final answer hides beyond every practical baseline. The same limitation applies to infinity. If space is exactly flat and has the simplest possible topology, then it extends without limit. That model is elegant and consistent with observation, yet another flat universe can be finite, with distant regions connected so that a path eventually returns to its beginning. If the repeating scale is larger than the observable horizon, no duplicate galaxies, matching microwave circles, or returning beams of light appear. The compact universe then looks identical to an infinite one from within the accessible patch. Increasing precision cannot solve a problem when the distinguishing evidence has not had time to arrive. A lower limit on size can become vast, but it never becomes infinity. Infinity is not measured by seeing very far. It is a claim that no final distance exists at all. Topology deepens the uncertainty because it concerns connection rather than curvature. Space may follow flat geometric rules locally while joining to itself globally. It may possess positive curvature and still allow several different closed arrangements. It may carry negative curvature within a compact structure formed by complex identifications. Each possibility changes the routes available to light and matter, but only if those routes are short enough to complete within cosmic history. The absence of detected repetition tells something important. It shows that no simple small topology has revealed itself across the observable sky. It does not show that every topology is absent. The universe can conceal its global architecture by making the fundamental scale larger than the region causally available. Inflation may explain why this concealment is so effective. A brief phase of accelerated expansion can stretch curvature and topology to scales far beyond observation. The visible universe may descend from a tiny region enlarged until its earlier shape becomes almost undetectable. This offers a natural reason for near flatness and for the broad uniformity of the microwave background. It also means that the same mechanism which explains the data may place the total geometry even farther out of reach. Inflation can make observable space look simple, while allowing the larger cosmos to remain immense, curved, connected, or varied in ways no present signal can disclose. The explanation does not settle whether space is finite or infinite. It may only explain why the distinction is hidden. There is also a limit in time. The observable horizon changes as the universe evolves. Light from some distant regions continues to arrive, revealing events that were previously unseen. At the same time, accelerated expansion pushes other regions toward permanent causal separation. Galaxies beyond the local gravitationally bound environment become increasingly redshifted and faint. Their future light may never reach the same observer. In the remote future, the visible universe can contain less evidence of the wider cosmos than it does now. Ancient microwave radiation cools and stretches, distant galaxies fade, expansion removes accessible landmarks. The total universe continues, but its history becomes harder to reconstruct from any one location. Cosmic knowledge does not simply increase forever. The geometry of space-time controls which evidence remains available. This possibility gives the present era a quiet significance. The sky still preserves the early plasma. The large-scale web remains visible. Distant explosions trace the changing expansion. Gravitational waves carry news of remote collisions. The universe currently offers several overlapping records of its geometry. These records agree well enough to support a coherent picture: a hot early phase, expanding space, structure growing from small fluctuations, late acceleration, and average spatial curvature close to zero. The picture is powerful because it joins evidence from different times and physical processes, yet its success should not be mistaken for completion. A model can describe everything observable while leaving global properties undecided. The unresolved questions are therefore sharply defined. Is the total spatial volume finite or infinite? Does space return upon itself after a journey too long to observe? Is the near flatness exact, or only the appearance of a curved universe with an immense radius? Does inflation begin from a larger geometry whose traces are erased? Are there regions beyond the horizon with the same average conditions? Or does the cosmos vary on scales no survey can reach? Current evidence does not choose among all these possibilities. It constrains them, ranks them, and sometimes makes one simpler than another. It does not close the final gap. Science often advances by turning broad mysteries into narrower uncertainties. The shape of the universe once belongs almost entirely to philosophy and imagination. Relativity makes it measurable. The microwave background turns ancient fluctuations into a geometric test. Surveys of galaxies and light refine the result. The conclusion that observable space is nearly flat is not a vague impression. It is one of the most carefully tested features of modern cosmology. The remaining uncertainty is equally scientific because it follows from the limits of observation rather than from a lack of method. The horizon is not merely the distance beyond which telescopes are weak. It is a boundary in the exchange of information. The final answer may therefore remain layered. Locally, space-time curves around matter and energy. Across the observable universe, the average spatial geometry appears nearly flat. Globally, space may be infinite, or finite without edges, or gently curved on scales far beyond sight. None of these statements cancels the others. They describe different levels of the same cosmos. The apparent contradiction arises only when local curvature, average geometry, total size, and topology are compressed into one word called shape. The universe may never provide a complete outline of itself to any observer inside it. It may reveal enough to establish the rules of the visible region while withholding the architecture of the whole. Ancient light reaches the horizon and stops. Geometric tests approach flatness and stop. Searches for repetition find limits and stop. Beyond each result lies another scale that cannot yet be crossed. The cosmos does not answer with a single image. It answers with a measured near flatness surrounded by uncertainty, a finite field of evidence opening onto an unknown extent. Its shape is not entirely hidden, and it is not entirely known. It remains a geometry partly revealed from within, while the horizon keeps the final answer beyond the last arriving light.